is relevant to the business process area, and also talk more specifically about an approach that we developed to business process customization that we call agent supervision. Yeah, so let me get going. Some of you may found, the introductory material a little bit something that you already know, but hopefully for some people this situates a little bit what the kind of approach that I'm presenting. So, yeah, so reasoning about action is an important subfield of AI, and it deals with how one can represent actions, plans, and processes, and how they change the state of the world, and also how you can reason about them. So some key reasoning tasks that have been investigated in the area are legality testing. So is a sequence of action executable in a situation? Also projection. So will a state condition hold after you execute a sequence of action in a situation? And also planning. So synthesizing a plan to achieve a particular goal condition in a situation. And of course, there are more general and more specific version of what, depending on the assumption that you make about the starting situation, whether it's fully observable or partially observable, and those kinds of things. Some of the key problems that have been addressed are, so there's the frame problem, so how do you represent action without having to specify explicitly what does not change when an action is performed. The ramification problem, how to represent indirect effects of action. Also the qualification problem, so how do you represent the conditions under which actions are executable. Again, without explicitly enumerating all the things that have to be, all the very exceptional conditions that have to be ruled out for an action to be executable. But many formulas that have been developed for reasoning about action, so the situation calculus, the set of action languages where you specify how the world changes. Also, high-level programming languages such as Golog and Convolog, where you can specify complex processes. We'll talk more about this. And problems about, there's been many solutions proposed. For the phrase problem, I think most people would agree that it's been solved at least under some conditions. For the others, there's still a lot of work being done. Some partial solutions, but in terms of reasoning method, well, one key method is regression. So this basically, to solve the projection problem, so or task, you want to check whether some condition hold after a sequence of action. Well, you can actually obtain an equivalent or a condition that will hold if and only on the initial situation that will hold if and only the query that you want to evaluate after the sequence of actions if this other formula held in the initial situation. So that kind of reduced the temporal reasoning to reasoning about the initial situation. Okay, so how is this work kind of relevant for business process area? Well, we think that the work in reasoning about action has been focused on reasoning and formal techniques. So we think you can use these to provide clear formal characterizations of problems that arise in the area. Also, some automated reasoning techniques that have been used in, for example, planning and so on, and it can be used to analyze and synthesize the process. How do you use this? So maybe for developing specification languages that have a clear formal semantic, for methods for verifying processes, also approaches process customization. I'll talk a little bit about that. So in this case, we're giving a process and we want to customize it to satisfy the client's constraints and preferences. Also, can be applied to these techniques can be applied to service composition, where you have a desired service and you want to synthesize it out of some existing processes, maybe by orchestrating them or choreographing them or and so on. Also approaches for monitoring and repairing processes. We saw a little bit about that this morning. And in general, techniques for dealing with knowledge-intensive business process as was described earlier. Okay, so the outline of the talk is I'll give it a bit of an overview of the situation calculus and combo knowledge. Then I'll talk about this approach to process customization, which we call agent supervision, that uses those. And this will kind of illustrate the kind of work that is done with these formalisms. If I have time, I'll talk very briefly about how you can do a kind of process orchestration in using this kind of framework, and then I'll conclude. Okay, so the situation calculus is basically a language of predicate logic, mostly first order, but with some second order features being used to specify the degree of situation. And it's for modeling dynamically changing world. So the main components are, so there's a constant S0 that represents the initial situation, and there's a function, little do, that basically denotes a situation that is the result from performing a primitive action or an atomic action alpha in the situation S. So basically, you can build terms that represent situations that follow sequences of actions being performed. And then we have predicates that are dynamic, and basically they take a situation argument. And we call these fluid. So, for example, here, this might be how one expresses that the robot is not holding anything in the initial situation, and in the next line, this says that after each robot performs the action of picking up object 1 in situation S0, it will be holding object 1. Okay, so the holding fluent, the predicate, sort of has a new, different value in the initial situation and in the situation that follows the action. Okay, so this is first order logic, so it's fairly easy for people to learn and so on. Also, there's a special fluent called POS, which is used to represent the fact that an action is possible or executable in a situation. So, to model a domain, dynamic domain in the situation calculus, we use basically a set of axioms that we call the basic action theory. So most of these axioms will vary according to the domain of interest. So whether it be emergency management or some sort of healthcare or whatever. So this includes action precondition axiom that determine or characterize when an action is executable under what condition. Also, successive state axiom that basically specify what is the extension of fluid in a situation that follows the performance of an action in terms of the action that was performed and what held in the previous situation. Okay? And this basically provides a solution to the frame problem. So basically you only need to specify what action action change the fluid, and all the other actions are assumed to not change anything. Okay? So because this quantifies over situation. And then of course you have some actions that describe what is true initially. There's some unique name axiom that allows you to say that actions with different names and different arguments have denote different actions. And finally you have foundational axiom that specifies three situations. So these situations represent hypothetical states that you can get to by performing sequences of action. So so that's the situation calculus. Then, of course, in many cases, you want to talk about not just sequences of action, but complex processes. So we've defined a sort of high-level programming language for representing complex processes or actions. So basically, you write a program to specify a process, and this comes together with a basic action theory that specifies the preconditions and effects of the atomic action you have in this program. Okay? So it's a pretty rich programming language. In particular, notice that we have some non-deterministic constructs. So either choose to do program delta 1 or choose to do program delta 2. These could be simple action or any complex process. Choose an argument for a binding to that variable x and execute program delta for that binding. So non-deterministically choose non-deterministic integration. We have concurrency, which is viewed as interleaving of the atomic action. There's also prioritized concurrency, recursive procedures, and so on. So this is a bit like, in a way, a procedural language that has some non-deterministic features too, but it's very different from a standard programming language where the actions are assigned to variable or following a pointer and so on. These are the atomic action corresponds to things that you perform in the domain and that change the state of the world. The transition semantics for a Congo log. So this is specified in terms of two main predicates. So trans says that you can go from, if you have program delta and you're in situation S, you can perform a single step on it to get to the new program delta prime, the remaining program delta prime, and the new situation S prime. And there's also the predicate final that says that program delta can legally terminate in a given situation. So using this, you can define complete execution. So capital do delta S prime means that there's complete execution of program delta that starts in situation F and ends in situation S prime. And so I don't think I have time really to go over how this is axiomatized, but if there's any questions at the end, we can come back. Okay, so that's basically a very quick overview of the situation calculus and Congo log. So for certain applications, it's interesting to restrict a little bit the kind of Congo log process description that you deal with. In particular, for example, if you're doing plan recognition, okay, well, if you observe an action and you know that the agent is execute this non-deterministic program, you would like to know a single remaining program after the action, okay, so that we have a single model of what the agent might might do next. Okay? So for this we use programs that we call situation determined. So that means that basically in any situation that's reachable in any execution of the program, if you know what the next action is, then there's a unique remaining program after that situation. So here we have an example. So this is a program that's situation determined because initially all you can do is action A, okay? And the remaining program after that is either do B or C. And then after you do B, then it's the empty program, and after you do C, it's the empty program. Note that this is still non-deterministic in the sense that, after I've done A, I can either do B or C. Okay? So on the other hand, the program at the bottom, it's not situation determined because if you observe A, okay, then either the remaining program might be B or it might be C. Okay? And so this is a hard model to work with if you're doing, say, plan recognition or, as we'll see later, customization. So, in fact, restricting attention to situation determined convoluted program, we can simplify a lot of things. So, we can define a kind of functional semantics, a predicate or a function, partial function next that says, well, if you execute delta in situation F to perform action A, delta prime is the remaining program, the unique remaining program. Okay? Of course, if you cannot perform A with that program in this situation, then we say that next will return undefined, bottom. Okay? So in a sense, it can tell you which action the agent can perform and what's the remaining program after he does any of those actions that are allowed. And for a situation determined program, this semantics with the original semantics are equivalent. We can also have transitive closure of next, so when you perform a sequence of actions, and this is the remaining program after that. So what does this give us? Well, in a way, it gives us that in the original for convoluted program, where the remaining program is not functionally determined but by the situation, well, you have to view execution as sequences of configurations which are pairs of programs in situation. For situation determined, it's essentially like a set of sequence of, an execution is a sequence of action. Okay? So you can think out all the execution, all the runs of your program as simply a set of sequence of action, or essentially a language of action string. Okay? So how do you define the semantics of this? Well, for example, for an atomic action, we would say that the remaining program when you do an action A and S is nil, so the terminating program if A is possible in the situation F. Otherwise, next is undefined. Okay? So here, if the primitive action is the action A. For non-deterministic branch, it would say, the remaining program after you do either delta 1 or delta 2 and do action A and F, it's what remains of delta 1, okay, after doing A and F, if delta 2 is undefined, okay, for A, or if delta 2 has the same remaining program afterward. Okay? So basically, here we want to, if you remember my little example with A and then B or A and then C, we want to rule out that kind of thing. So we want to say that they're undefined because, if you do A with delta 1, you get B remaining. If you do do A with delta 2, you get C remaining. Okay? So this would not satisfy the condition here. Okay? This is similar for delta 2, so the remaining program will be what delta 2 says if delta 1 cannot perform A. Okay? And otherwise, it's undefined. So this is just to illustrate how we define the semantics of the situation determined program. And basically, what we want is that if the remaining program is not uniquely determined by the action, it always returns undefined. Okay, so a nice thing about situation determined program, as I said, was that they can be characterized by a set of action sequences that they generate. And so we can define the set of partial runs of the program delta situation as simply the set of action sequences that don't return undefined, okay, as the next program. The complete runs are those like the partial runs that end in a final situation, and good runs are the partial runs that can be extended to a complete run. You can get the computation tree if you want from the set of runs. When we put this restriction to situation determined program, then we can, define sort of the usual set theoretic operation or language theoretic operations on sets of execution. So union is just the non-deterministic branch. So this program has the union of the action sequences of delta 1 and with the set of action sequences of delta 2. We can do intersection quite easily. Essentially, this is a kind of synchronous concurrency construct. Okay? So if both delta 1 and delta 2 do the same action, okay, all the way, this gives you a run of the intersection. You can also do difference quite easily. So this will basically, this construct minus delta 1 minus delta 2 as the executions of, instead of executions are those that are executions of delta 1 but are not executions of delta 2. Okay? And then complement is you basically you define it in terms of minus and the program that produces all of them. Okay, it should be interesting to see too that any convolute program can be made situation determined if you add certain basically decision actions. So if you remember my example that was not situation determined, well, if I add some action to say explicitly that, you're choosing to go left or you're choosing to go right, you're making a decision, then it's easy to, and there's a systematic way of doing this. Okay? So that's basically, this new restricted class of programs called situation determined programs in their property. And now we're going to use this to do a model of service customization. So let me first give a little bit of context to this. So there's been a very influential paper by McIlraith and Son in 2002 that proposed an approach to automated service composition. And this basically involved first writing very generic procedures for performing tasks. Okay, that are very deterministic, non-deterministic. So they include a lot of different alternatives. Pretty much all the alternatives you can think of. Okay, and she used convolute to express those, but you could use some other similar, formalism. And then you want to customize them to satisfy the client constraints. So you you basically obtain your composed service by customizing these generic procedures. And later, so this work was generalized to support linear time logic, temporal constraint, and also preferences. And the way these were handled were basically by compiling them either to Convolog or to a decision theoretic version of Convolog, where you kind of can do, maximize expected utility. Okay. So and these are always evaluated over a finite horizon. So, and just to give the idea, you might have, say, for booking a trip, a procedure, a generic procedure that says, well, either you book a package or you book a simple trip or a complex trip. A simple trip is simply booking a flight and booking accommodation. For booking a flight, well, you have to pick an airline, pick a flight by that airline, ensure that it's suitable for the customer, and then book it. Okay? And flight constraints might be something like always choose hotels that are at least 3 stars, always book your flights on a Star Alliance airline, and at the end I want my cost to be less than $2,000.
So can I ask you something? In this HTL specification, these are on finite strings, right?
Yeah. So the compilation is over the finite execution of the server. Okay, so basically this kind of is a bit of a motivation for our work. I mean, it's not the only thing. Many people have expressed, we want to be able to configure processes or to customize them according to the client's needs. So here's an approach to doing this that we call agent supervision. So the idea here is that we have a process that does not always do what we want, like a child. Okay, and we want to restrict this child, supervise it so that it remains good. It performs only safe behavior. So on the other hand, we don't want to unnecessarily restrict the autonomy of this child. We don't want to lock him up or anything like that. And what can make this a little bit difficult is that some of the actions of the child may not be controllable. So others, you can simply say, you can't do this, you can't do that. But for others, you sort of have to, the child may do them even though you don't want them. So basically what we want to do is to synthesize some sort of controller or supervisor that, gets to see what the sequence of action and the next action that the agents want to perform, and says, well, if it's a controllable action, you can say, no, you can't do that. If it's an uncontrollable action, it will occur anyway. Okay? So this is the classic problem in discrete event control, and it's related to synthesis planning, but we'll be a little bit, how this goes. So our approach is basically we want to use the situation calculus and Convolog to specify behavior. We're going to restrict attention to situation-determined program, and the key result is that we're going to show that there's a unique, most permissive supervisor for any specification for a behavior. And we're going to basically show different ways of representing this in Convolog. So the assumption is here we have two agents. One supervised. We assume that it's represented by program delta P, and there's a supervisor, which is essentially the specification that we want to import. We're going to assume that it's also represented by a program, okay? But possibly a very non-deterministic program. That only rules out a few things. Okay? As I say, previous work shows that over finite runs, I mean, you can compile a declarative specification of the constraints into such a program. And so we want S to be supervising V so that it remains within the constraint that S has, but otherwise you can act as freely as possible. So an example of this is, so the program of the V1 here specifies that agent V can repeatedly pick an available object, repeatedly use it, and then discard it. But if the object may break, and if it breaks, then immediately afterward, it must be repaired. Okay? So this might be something you see in sort of manufacturing or context. And then afterward, it discards it, and it can pick another available object. So suppose we want to constrain this agent so that as soon as it breaks, that it never breaks an object more than once. Okay? So basically, we can specify this using this program. So pick an available object. You can do 0 more actions that are not break and or discard. If then you can discard it, or you can, if it breaks, then you cannot do. You cannot do a break, and you or discard, and then you discard it, and you get a new object to continue. Okay, so when all actions are controllable, it's very easy to come up with the best supervisor. Basically, it's simply the intersection of the behavior that the agent has of the B and the constraints imposed by the supervisor, the delta S. So for here, this would say, we could express this with this program. It says, pick an available object, use it 0 more time, then you can either discard it or you can break it, repair it, continue to use it, but you cannot break it again without discarding it. Okay? And you know, intersection is defined in our language, so it's as I say, it's synchronous concurrency. So, so this is all straightforward. If you have a controllable action, then you know, then it becomes more tricky to design a supervisor because the supervisor cannot prevent these actions from occurring. Okay. For example, if we let a child out in the garden after it is raining, then once he's out, there's nothing to prevent it from you know, playing in the mud and getting muddy. Okay. So this gives a bit of the intuition, and so we want to get the most permissive supervisor that copes with this. So we can use a special fluent AU that says that an action, a little AU here, is uncontrollable in situation F. So this is how we specify what uncontrollable. Everything that does not satisfy this is controllable. So how do we want to address this? Well, basically, in general, you have to do a kind of look ahead. So here in this example, if the action U1 is uncontrollable, okay, and we want to prevent its execution, so basically you cannot allow the agent in the starting state to do A2. Because if he does A2, then you're going to get to this situation, and then it may do a U1. So you have to, here you have to say that the only allowable action for the agent is A1. Okay? But we want to do this as little as possible to ensure the constraint. So basically, So by one and then ram it. So basically, we can say that you know, a supervision specification is controllable for an agent delta B in a situation if basically whenever you add an uncontrollable action to a good run, if the agent may do this, so he's happy with that, then it must also be good for the supervisor. Okay, it must also satisfy the constraint. So basically, if you have some sequence of action in a good run for both, and AU is uncontrollable after you do these actions, if the agent likes this run with this added action, then the supervisor must be happy with it too, delta F. Otherwise, that means you've gone off, you know, you violated the specification. Basically, we want the supervision specification that's controllable and ensures the desired constraint, but leaves the agent as free to act as possible. So what we want is a maximal permissive supervisor, and we can show that such a supervisor always exists and is unique. One way to define it is in this way. Maximal permissive supervisor for a behavior delta B with specification supervision specification delta S in this situation, you can basically obtain it by taking the union of all the set E's, okay, where E's are a set of complete runs for both of the agents, okay, and these sets are controllable. Okay, so basically, now this makes use of a bit of a funny construct. This is set E is like sort of a bit like a non-deterministic branch that can take an infinite number of sequences of action as arguments. Okay, so it's not really a realistic programming language construct, but it allows us to, if we add this to our formalism of complex action, then we can easily specify this maximal permissive supervisor. And so we can show that this maximal permissive supervisor as defined always exists and is unique, that it's always controllable for the agent that we have in the situation, and basically that it's the one that leaves the agent most free to do what he wants. So basically, if we have any controllable specification delta add F for the agent, and this is a subset of its complete run, is a subset of those of delta B and delta F, well, it must be included in the complete runs that we obtain by running delta B and the most permissive supervisor. Okay. So, for example, here, suppose for our previous example, suppose that we have a break action that's uncontrollable. Then we want so this means that the supervisor cannot prevent the agent from breaking the object a second time. Okay? So if we want to ensure that objects are broken at most once, okay, then we must force the agent to throw away, to discard the object as soon as he has broken it and repaired it. Okay? And this is what so the MPS amounts to using this specification for the process. We can also introduce a concept in the language which is sort of like the intersection but takes the uncontrollable action into account. And the definition here that basically has exactly the same set of complete run as the MPF. So this is a more classical programming language construct. Okay, so what have we done here? Well, basically, we defined this situation determined combo log that had a similar semantics and was closed under language theoretic operation, and where actions, basically the execution of that, the program could be used basically as action sequences, and we've shown that we can get, you can customize it, but by restricting as little as possible its behavior by obtaining a maximal permissive supervisor. And we've extended the language to Convolog to specify that. So basically here we're generalizing some previous work in this three-event control to first order logic-based infinite state languages. And also we allow action controllability to depend on the situation. So there's a lot of future work with respect to this. So what we have essentially is a model of supervision. So in terms of deciding maximum permissive supervisor, we need to have algorithms for that. Now and probably the program, I think, is undecidable in general, so we want to look for special cases. For the finite state case, then we can use some of the techniques that have been developed for the discrete event control area. So basically, this is this approach to modeling composition in our framework. I'll go very quickly over just to give another example of the kind of work we've done. So process orchestration. So basically, you want to control the set of available services, controlling who gets to execute next to produce the desired service. So one model of this that's been developed by Giuseppe and Sebastian Sardinia, services are specified as transition systems, and they assume that the desired service is deterministic, and so for a current state in an action, then its next state is determined. Okay. But the available services need not be deterministic in this sense. So they may choose to go to a next state which is not in the control of the orchestrator. Okay. So basically, we say that the orchestrator realizes the desired service. If for any run of the desired service, the orchestrator can tell which select an available service, have it perform the same action that the desired service wants to perform, and continue to do that indefinitely. So an example from Muragi et al. Is suppose the desired services you want to be able to 0 more times either search for, say, a song by author or by title or book, and then listen to it. And you have two services, one which allows search by authors, another one that allows search by title. Then you can orchestrate these two to perform the desired service. Basically, if the first action is search by author, you select service 1, and the list goes to the same service. And similarly, if the first action is search by title, you select the second service. So this is sort of a definition of orchestration. So what we've done is developed a sort of game theoretic framework or logical framework based on convoluting the situation calculus that can model this kind of problem. So basically, there's a lot of problems that involve, synthesizing behavior where, some aspect of how things go is not controllable. Okay, this could be a general multi-agent setting, like a game, or it could be, this service orchestration where you don't really determine what the available service, what state it will go to. Okay, so basically the framework that we've developed for this is so it's based on situation calculus and Congo log. We define what we call situation calculus game structures, and there we specify, we have a new fluent, a special fluent, legal that specifies what situation or legal game situation. And as part of this, we have a kind of turn taking. So we assume that in any situation there is one agent that's in control. Okay. Game log is a variant of Congo log where you can use to specify what are the legal game situations. Okay, and basically it's similar to Congo log, but here, when all the choice points are annotated with which agent is controlling the choice. Okay, so it's a little bit like situation determined Congo log, where we have choice decision actions whenever there's non-determinism, and we say which agent is making the choice. So if the game is tic-tac-toe, well, when is agent X turn and what is choices are? Okay, and these get represented as choice action in the situation. And then the other thing we use is calculus for specifying properties that we want to verify, as well as ATL or alternating time logic style operators. So we can say this example here is basically, so this says that the agent M can ensure that eventually he wins, and this is expressed in calculus in this way. So either the least steps that either you win now, or after M can ensure that after one step it remains in that step. Okay. The reasoning techniques that we used for doing the verification involve regression, doing fixed point approximate, and if you're using game goal log characteristic graph, which are kind of an abstract version of the kind of graph that you have in model checking. And so these techniques, they're sound. In some cases they work. We found, many interesting problems where they do work. In other cases, they're incomplete. So process orchestration, we can basically specify it in this kind of language as so the game would be the scheduler agent. It controls the concurrency between the desired service. So basically here the desired service, this is the desired service agent. It chooses some action that it wants to perform, and then the available service, the scheduler will choose one of them to perform the action. Here we modify the desired service so that basically it doesn't perform the action, it requests it, and whenever the action is performed for real by one of the available services, this gets cleared. And so we can say that for the orchestration task, we want to show that this formula is entailed by theory. So basically that the scheduler can ensure that basically, all the actions that are requested by the desired service are performed, and that all of the processes, reach a terminating state. So the specification is a little, basically this depends on this requested action fluent that keeps track of the requested action, and when some available service is performed, then it becomes nil. If it performed a different action, then it goes to the error state and stays there. Okay? So this is how we ensure that the action that the desired service wants to do are always made. And here we ensure that this is the case. So no matter what state the available service choose to go to after performing some action, we can continue to basically perform the desired service. Okay, so that's my last slide. Basically, what I've tried to show is that the situation calculus and Convolog provide a rich logical framework for modeling, verifying, and synthesizing processes and services, and that these are especially relevant for the kind of processes that we're focusing on in this workshop, processes that occur in complex, dynamic, and completely known domain. And we've illustrated a little bit with this process composition, orchestration, and customization approaches, how you can use these frameworks to deal with some of the problems in these areas. But the key thing, I think, is that these frameworks provide a way to formally characterize the problems and exploit some available automated reasoning techniques. In the panel, I'll say probably more about other problems that can be dealt with. Obviously, there's planning technologies that can be used and so on. Okay, so that's it. Any questions?
Concerning the first part of your talk, the part with the controllable actions, do you have any implementation of that?
No, we don't. We don't. So, as I say, implementation for the finite state cases, the existing approaches that are based on model checking can be used. Okay, but for the general case, so we would have to look at the restricted version of the problem to guarantee that we have a solution, or look at the approaches that sometimes that are not complete. Okay? And this is future work.
You were concerned the synthesis of the maximal permissive supervisor. And if I recall the theorem, you need a complete run of the agents involved. In case you don't have the complete run, you only know up to a certain distance in the future. Do you have similar results, or?
Well, we think that there's a specification that specifies, what the behavior of the agent is, including the complete run. Now, I guess the definition we have deals with agents that terminate. So if you want agents that will run indefinitely, then you have to modify the definition.
Right. So let me say something about this. So you have a specification of the entire set of runs, which obviously is infinite. Okay. And what you synthesize is prefix closed. So every prefix is already good. Okay. And it's going to continue to be good. Okay. And then it's true that you don't have any infinite run. Okay. So this is a terminating setting. It's not a setting where you don't.
And if you only know properties, in instead of knowing the actual future or possible futures, you only know properties about this future. So to speak, for example, the child will not leave the room, but I don't know when he's going to move within the room. Something results about this kind of thing, so to say.
That's fine, because it means that there will be an arm which moves in every place, right? So this is already considered. Because it's a set of arms. It's a language. It's the language.
Other question? I have one. You said that the part on the babysitting is only functional, and you said that you can think to implementation only in limited settings, right? How complex is it? Because I'm seeing that very interesting for the enactment of declarative processes. There is a lot of hype these days in declarative processes. So I imagine something like this. You have the constraint of the declarative process, and the enactor, you want the user working with it, let's say. So he has a kind of dashboard in which he reads what he can do. But then you want the system stopping him if you're doing something that is not allowed from the constraint. How?
Well, you have to do look. I mean, system control. You have to do some look ahead, and so I mean, the definition we have is, you know, it's well defined, but so this definition, except that you know, this requires searching forward for what the behavior might do, okay, and ensuring that you know, to decide whether you want to allow this next action, you have to look ahead to see what to be, if some sequence of uncontrollable action that the behavior might do that is not no good for the specification. Okay.
Okay. So the definition is the okay. You can speak up.
And you can do this kind of online, and then you may come to a point where you simply have to block the agent from doing anything, because the next thing, you know, in my example here, so say you executed the agent for a while, and then it got to the state at the top here. So there you can say, well, you can do A1, but if so there you're going to terminate. But in general, I mean, it may be that I have some other example. Yeah, so here if you look at the C example, so here it would say, well, it's okay for the agent to do A2, okay? Because afterwards, but then once it gets to this state, then it would say, no, you cannot do anything. Because if I let you do A4, then you might do A1 after that, okay? So to solve this, is to realize here that you cannot really allow A2 and terminate, then you have to do some more look ahead. Okay? So this is you have to use like the search operator in go on over this synchronous concurrency with uncontrollable actions.
But if I have some probability that I know the incredible probability, maybe I can read something.
Okay. Yeah. Well, so you know, as you saw in the definition, the definition is perfectly fine. It's just that you know, you know, to search forward to see whether there's any sequence. If you only have small sequences of uncontrollable action, then it's probably doable. But in general, you know.
Yeah.
Any other questions?